With a surface area of 150 square miles, Utah Lake is one of the largest freshwater lakes in the western United States. Utah Lake has played a key role in agriculture and the economic development of northern Utah during the past 150 years. Here are some of the past key actions and management decisions regarding Utah Lake. Overharvested native fishes, introduced carp, diverted water, built sewage treatment plants. What is TSSD? TSSD stands for Timpanogos Special Service District. We clean the sewer water for over 250,000 people in our growing community in northern Utah County. We remove greater than 98% of the primary pollutants and process about 1 pound per day of biosolids for each person, which is 250,000 pounds every day. There are 7 other treatment plants that flow into Utah Lake. Together, these plants clean water for about 650,000 people. That number is forecasted to grow to 1.3 million in the next 20 years. These plants are publicly owned treatment works, or POTWs. POTWs in Utah collaborated with the Utah Division of Water Quality, or UDWQ, and Utah legislators to set a reasonable and attainable level of discharging no more than 1 part per million phosphorus into Utah Lake. This resulted in a new Utah law, or rule, in 2015. The rule, along with expansion for growth, will take 10 years and hundreds of millions of dollars for full implementation. All the treatment plants on Utah Lake will be in compliance by 2025, after which a thorough review of the impact of the lower standards, or in other words, a return on investment study, should be conducted. By incorporating new processes, TSSD achieved this standard in 2020 and currently removes over 80% of the phosphorus that comes into the plant. Calculations show that at the current growth rate, with these processes in place, the 2070 population will discharge the same amount of phosphorus to the lake as was measured in the 2015 population. This buys us time to do research, and we are doing the research. Now the Utah Division of Water Quality, or UDWQ, is collaborating with the Utah Lake Authority to set even lower site-specific nutrient standards for Utah Lake. Their work is known as the Utah Lake Water Quality Study, or ULWQS. Will these levels achieve a cleaner lake? How will clean be measured? How clean is clean enough, and can it be achieved? There is a perception that cyanobacteria blooms in Utah Lake are getting worse. This is a graph of the algal blooms from 1995 to 2018. While there may be a perception that the algal blooms are increasing, this UDWQ data shows that the line is flat, or in other words, there is no growth trend or discernible increase. Safety warnings have been issued and the lake shut down multiple times in recent years because of harmful algal blooms. What is causing these blooms? One thought is that they are caused by high amounts of nutrients in the lake, and that lowering nutrient levels, particularly phosphorus, will solve the problem. Will lowering nutrient levels decrease cyanobacteria? In 1934, Alfred Redfield published a paper about his data and analysis of marine biomass, which he collected during several voyages to oceans around the world. He found a remarkably constant ratio in the elemental composition of marine organic matter. The atomic ratios of phosphorus, nitrogen, and carbon were the same in all matter he tested, whether living or dead. The discovery was named after him as the Redfield ratio. The ratio is here simplified to P to N to C equals 1 to 10 to 100. Since nitrogen and phosphorus are considered the most limiting to plant life, it is thought that by limiting one of the elements in water bodies, such as phosphorus, will reduce or eliminate the growth of phytoplankton, which is all the green stuff in Utah Lake. Cyanobacteria, a type of phytoplankton, come in all different sizes and some produce toxins. Directly testing for toxins is a good measurement for determining the toxin level in Utah Lake. The excessive nutrients in Utah Lake come from multiple sources, including sediment resuspension, surface runoff, air deposition, and discharged water from treatment plants. Let's take a closer look at those 4 primary sources. Sediment resuspension. It is estimated that Utah Lake has 1,500 tons per year of phosphorus released into the water column from lake sediment. Wind and wave action in the lake constantly mixes things up. That mixing is referred to as sediment resuspension and makes phosphorus available for algal growth. We are studying carp mixing, ecology sediment stabilizing, and the ability of Utah Lake to sequester the suspended phosphorus and make it unavailable for algae food. Surface runoff. The surface of the earth throughout Utah Lake's watershed used to be the lakebed for Lake Bonneville. It is rich in phosphorus. Precipitation causes surface runoff, which brings a continuous flow of phosphorus into the lake. The Wasatch Front Water Quality Council, which is a collection of POTWs, has been collecting data on this since 2014. Last year, 42 tons of phosphorus entered Utah Lake from surface runoff coming from tributaries. Air deposition. In addition to nitrogen, oxygen, and other gases, our air is filled with airborne solid particles. When these airborne particles are washed through snow or rainfall, or fall as dust into the lake, this is referred to as air deposition. Air deposition can be observed in two ways: high air deposition or local air deposition. High air deposition can come from faraway places such as West Coast fires or even from other continents. Local air deposition comes from wind-blown sands and local pollution. Sometimes air deposition makes the news. On February 5th, 2021, residents in Utah County noticed large amounts of brown snow covering everything. This is air deposition. One nice thing about precipitation is that it cleanses the air. The downside is that the air is often filled with things we don't want in our water, such as pollutants and excessive minerals. This memorable one-day event brought about 5 tons of phosphorus into the lake. The Wasatch Front Water Quality Council has sponsored research since 2017 to measure as much as 77 to 430 tons per year of phosphorus entering Utah Lake through air deposition. Treatment plants, or POTWs. This table shows the phosphorus load to Utah Lake by treatment plants on Utah Lake in 2021 and projected loads after 2025. Treatment plants on Utah Lake contributed 124 tons of phosphorus in 2021. By 2025, it will be about 53 tons per year. This represents a fraction of the total phosphorus in the lake. Let's add all this up. The lake has about 870,000 acre-feet of water with 0.07 milligrams per liter of phosphorus. That multiplies out to about 82 tons of phosphorus. In 2021, sediment resuspension, 1,500 tons. Surface runoff, 42 tons. Air deposition averaged 254 tons. And treatment plants contributed 124 tons. That is a total of over 2,000 tons of phosphorus in Utah Lake. Phytoplankton are indifferent about the source of their nutrients. If we remove the nutrients from just one source, treated sewer water, will it change how the lake functions? The 2015 rule reduced phosphorus coming from POTWs by 80%. We need a cost-benefit analysis to see how the hundreds of millions of dollars invested by POTWs helped the lake. Did lowering phosphorus coming from treatment plants translate to fewer algal blooms? TSSD and Utah Division of Forestry, Fire, and State Lands commenced a study titled A Sustainable Approach for Limiting Harmful Algal Blooms in Utah Lake, which we generally call the Limno Corral study. Other agencies have inquired about the project, for example, the DWQ and DNR, and want to work with us on the study. The following is a summary of the 2022 study. We reported in 2021 the struggles we experienced maintaining the integrity of the Limno Corrals, made difficult from turbulence caused by wind and storms on Utah Lake. This year, all the Limno Corrals withstood all the storms. Here is a summary of the long-term holistic solutions we are probing in the research. Deep water, 6 feet and deeper. Binding all the phosphorus. In binding phosphorus, we are sequestering the phosphorus so that it is not available for food for algae. Lake mixing. For lake mixing, we are assessing mixing impact and correlating it to carp mixing, wind, and how turbidity may inhibit light in the water column. Carp and nutrients. For carp and nutrients, we are assessing the presence of carp, nutrients, and their effects on water quality. Aquatic vegetation and carp. For this part of the study, we are assessing the effects of carp, nutrients, and vegetation. Aquatic vegetation and other fish. For this area, we are assessing the effects of fish, nutrients, and vegetation. Shallow water, approximately 3 feet. Aquatic vegetation. For aquatic vegetation, we are evaluating the vegetation to stabilize the lake bed and regulate nutrients. Mollusks. Under mollusks, we are assessing the stabilizing effect of the presence of mollusks and their contribution to filtering and cleaning the water. Mollusks and aquatic vegetation. For mollusks and aquatic vegetation, we are assessing the effects of mollusks and vegetation combined to synergistically restore the lake's ecosystem function and maintain and improve water quality. Aquatic vegetation and carp. For this area, we are assessing the effects of carp interaction with aquatic vegetation, including juvenile carp recruitment. A few final thoughts. The research season ends in October and data is still being collected. The experiments are underway and are establishing a baseline. While statistical data will be forthcoming, visual observations are encouraging and show that some of the options reduced or eliminated turbidity and cleared the water to the bottom. Also, there is a learning curve to this project. One of the failures was the introduction of fish to the Limno Corrals without bird netting. Birds found they could see the fish, so they perched on the edge and easily harvested the fish. We need to maintain netting to keep birds out, which is one of many corral design improvements made over the past year.